in those other coordinates which we use here. And when you do that, you get two 1D Schrödinger equations, one for psi and one for eta. And what is important here is that the motion in psi is, this is the field-free one, this is the field rest potential. So you see, in here where the initial bound state is, there's not a big change in the potential. This is one of the key physical inputs into this theory. In fact, what the field does is that it even increases the potential, so it increases the binding in this one coordinate. The other coordinate, on the other hand, in our notation, the eta coordinate, we have this one when there is no field, and when there is a field, we have this one. So here you have the tunneling barrier. So in the theory, you go into parabolic coordinates and consider the tunneling problem in these coordinates. And this is also what we this is also what we want to do in the case of molecules, because if I have some molecule here and I take out an electron, asymptotically, it sees a Coulomb potential, right? So if I take one electron out from any system, if it's far enough away, it's still a Coulomb potential. It's just the monopole that survives. This means that asymptotically, we always have this separation. And this is a key point when you read the theory. Here I plotted some equal value surfaces or lines in the xz plane for a fixed eta, such that we can see how this curves look. And in particular, if z is large, negative, which means in the tunneling direction, here eta is more or less minus 2 times z. Okay, so now it's getting, now there are really technical slides here. So this one here we all know, this is just a Schrödinger equation. And this one here you don't know, most likely, but it's easy to get because the only thing I have done is that I have re-expressed this kinetic energy operator and the other coordinates here in terms of these parabolic coordinates. And then I have a differential operator with respect to eta, and then I have some other factors here depending on energy and field. And then I have collected a bunch of terms in this operator, which is a function of eta, as a parameter, but it's really an operator of psi and phi. Why do I do that? I do that because then I can, for example, choose to work in a basis where I pick a fixed value of eta and find the eigenvalue and eigenfunction for this one. This we call an adiabatic basis. And asymptotically, this operator here, in fact, becomes independent of eta, so I can define asymptotic channels. This number, so the point here is that up here, this is like an adiabatic parameter. This is like capital R for like in the von Oppenheim approximation. But here it's the tunneling coordinate, which is true. Down here it disappeared because this operator is independent of eta at large distance. And then I have a channel. So this channel here is nothing else, and you see it's a channel which is a function of psi and phi. So it's nothing else but this new index is nothing else but a specification of where am I in this psi coordinate, right? And then when I have such a basis, I can, of course, completely generally expand my statement that this is also without approximations. This is like, if to make a parallel, you can think when you want to do a molecule, you can have, for example, von Oppenheim states here, and then you can expand the full wave function in von Oppenheim in a complete set of von Oppenheim states times initial wave function. It's exactly the same. A complete basis, and then unknown expanding coefficient. And then I can insert this into the Schrödinger equation, then I get a new Schrödinger equation for the unknown functions. They look like this. Each we solve ab initio. But to analyze it, we can also look at large distances. And this, then these terms here disappear, and we only have this term here, which is without any couplings. So this is also, of course, important to have no coupling at large eta. And then, since eta here is large, we can ask ourselves, how does the solution look like at large eta? And to find such solutions to such differential equations at large eta, for example, in this case, there is various techniques. There is a technique called method of dominant balancing, which is a nice technique. If you apply that technique, you get this solution. And if you don't want to look up how to use that technique, you can also verify it, because I've now told you this is a solution. And if you don't trust me, you can take this and insert. But of course, if I hadn't given you this, it would be difficult to figure out what to insert into the equation. So there are techniques to find this type of flow. And now we're almost there. This was my general expansion, a function of eta, a function of psi. The function of psi was expanded in all the channels. And this square root here I just include because it makes the differential operators more convenient. So now at this point you may stop and say, what on earth is he talking about? I wanted to calculate the rate. Where did the rate go in all this discussion? And this is now these equations here that tell you about the rate. So of course the rate here, so if now this is positive z and this is negative z, then I want to ask what is the number of particles per time that go out here in this direction, at large negative z. It's the integral over the current in that direction with a minus, and then I integrate over a plane perpendicular to that direction. So I need to calculate the current. I know the formula for the quantum mechanical current from my quantum mechanics course, and then I have to use a chain rule to express this differential operator in terms of eta instead of z. And then I also have to know something about this area here in the new coordinates. And this I did for you here. And then one possible task, if you want, is to take this wave function here, calculate the current, calculate the integral, and then you obtain this result. This means that in this tunneling theory, this function here is the important object. So this is now what we want to get. And now it's getting really technical, and there's no way I can tell you how this can be done in a 1 hour talk. So there, for the interested reader or listener, I refer to the paper again, and I now give you the recipe of obtaining the result. The recipe is that you should take the solution here that we have obtained as a general solution, and you should then look at it in the classically allowed region, which was the region out here. Out here. Then you can actually solve for this unknown function out there. And then you continue that solution to the classically forbidden region, which is here. So there's a way to do that. We can discuss that this evening if you like. And then now you have the solution here, and then you match that solution to the initial bound state, which is this object here, which of course also now has to be expressed in these new coordinates. So all this can be done, and with these instructions, it's possible to verify these equations, which are the central equations in that paper. I just did this before this talk to make sure I could still do it. So it's possible to do. Now, and the end result is this. So now in this equation, if I take the norm square of this, it is the rate in a given channel. So let's just look at that rate in a given channel a little bit. What we get out from that equation. If I take the norm square of this, I get the rate of going into that channel nu. So it is, say, d nu squared, and then it is e to the minus 2 kappa nu z e to the minus 2 kappa cubed divided by 3f and some other terms here, right? And all of this here, with these other terms, is just a simple function of the field. Let's call that WDF, the field factor. And then the rest here is a molecular property. It tells you something about if the system has a dipole, how is that dipole oriented with respect to the molecule. You see, if this mu z, which is the z component of the molecular dipole, is positive, it meaning that the dipole is in the same direction as the field, it's more difficult to ionize. So this here is related to the energy shift. And then this one here is related to the asymptotic form of the wave function here. So this here is the asymptotic coefficient. So these two here, these two guys here, we call maybe capital G, mu, and we call that the structure function. So in the tunneling theory now we have actually identified in this leading order that we always have a field factor and we have a unique molecular specific factor. And this is now a property which is unique for any molecule. This means that you can calculate this and put it into tables, if you like coalescibility to dipoles. So this we have done it for maybe 50 different diatomic molecules. We have a catalog of all these structure factors in atomic and nuclear data tables. To give you some more physics on this, I think it's also nice to make this drawing here again. I make a drawing here. Here's the effective potential. And I now want to investigate two cases. So here in case A, I have a molecule oriented like this. In case B, I have a molecule oriented like this. In both cases, the field is in this direction. In this case, the dipole is like this. In this case, the dipole is like this. Because the definition of the dipole is that the dipole goes from most negative to less negative. And this was an attempt of showing a lot of electrons here on this end and not too much on this end. And the opposite. So in this case, the field and the external field of the dipole in the same direction, it means that the ionization potential is larger because of the lowering of the energy. So it should be more difficult to ionize if I just look at the tunneling exponent. In this case, it's opposite, because here the field is like this and the dipole is like this. I have a raising of the energy. It's easier to ionize. But there is another effect, namely that here you have a lot of this. You have a lot of density close to the tunnel exit. So this is what, now I have discussed this geometry and energy shift. It's just to show you, or tell you, that it's not just the phase, it's not just the exponent, it's also, in fact, this object here, which tells you something about how that object looks like at large distances. So this is what I wanted to tell you about this weak field asymptotic theory. And this is the formula that you can use most often, and where you have this structure factor and you have a field factor, which is essentially the one I just showed you. And the nice thing about that is that it is consistent with all the other correct theories on the market. And I think due to time we skip this now here. So this is just a summary of the formulas. We can also calculate a lot here. If any of you, how many of you are from time to time using quantum chemistry codes? One? Yeah. Okay, so in a quantum chemistry code, you work with Gaussian orbitals, or Gaussian basis sets. How do you think Gaussian basis sets, how do you think do you think they're good at representing stuff that is far away from the origin? No. You don't, and this is one problem. So this type of theory that relies on things that are far away from the origin requires careful quantum chemistry treatment. But we have in our department Frank Jensen, who is a very good quantum chemistry person, and he has some techniques to get stable behavior. So you don't need to know what is on those nucleons. It's just illustrating that if you just use quantum chemistry programs like a black box, you run into problems. But this you would do with any type of tunneling theory. One small note here is that the same formulas can be written up, in fact, for an n-electron system. So this is now a many-electron theory of tunneling. And the formulas look the same, and you can also look at this like abstract Picasso picture. It's not important exactly what it is. The important thing is that it's the same as before, essentially, except that the orbital, which is now coming into the theory, is the so-called Dyson orbital, which is the overlap. Well, it's not the overlap. It's what is left after you have integrated n-1 electrons out from an n-electron wave function. So, then I want to spend the last couple of minutes discussing nuclear motion. And here I will spare you from the derivation of formulas, but more give you the hope to give you some physical feeling of what can be expected. So, we have in AMO physics many situations where the Born-Oppenheimer approximation is extremely accurate. We can calculate ground state energies to any precision, basically. But we also have at the same time a series of manifestations when the Born-Oppenheimer approximation break down. So, as you know, for example, we can take this last example here. So the Born-Oppenheimer breaks down in Rydberg space. Why is that? It's because it's assumed in the Born-Oppenheimer approximation that the electron moves fast compared to the nuclei, which moves slow. But if the electron is in Rydberg, it's also moving extremely slow. So then, eventually, it will move maybe even slower than the nuclei. So you could have inverse Born-Oppenheimer. But anyway. And there are also other cases here at avoided crossings and conical intersections. These are all manifestations of the same thing, namely that the energy separation between the electronic energy levels become very small and comparable to typical energy separations in the nuclear bubble. And now the intriguing point that I want to make here is that in fact in tunneling, you will always reach a regime where the Born-Oppenheimer breaks down for particular field strengths. So to do that calculation, we chose a simple model. So because this we illustrated initially in the model. So here we have the nuclear motion, and here we have the electron motion, and here we have the Schrödinger equation for the combined system. So this is now coming back to one of the questions. So this is the kinetic energy operator of the electron, this is the kinetic energy operator of the nuclei, and these are the potentials and the interaction with the external field, and this is the energy that we are, which is now a function of F and therefore complex. So therefore the solution should be on this form where we have this gradient. And then when we did some calculations, well, okay, for some technical reasons it was easier to use some good approximations to the H2 and H2 plus curves. And then we got these results here. Let's focus on the top view graph. Here I have the field strength. Here I have the rate divided by this field factor, which I have over here on the whiteboard. This curve here is the exact result for this number here as a function of field strength. And then I have also our theory, this weak field asymptotic theory, can also be extended to include nuclear motion. It's the blue one. It's not too bad. And then we have the Born-Oppenheimer approximation, which is okay at large F, but breaks down here. Maybe you would say it breaks down here and behaves badly at lower field strength. And this effect is also present at higher nuclear mass, but it happens, and it happens even earlier in field strength. So this is what came out of this, and then now I want to explain what is the physical origin of this. breakdown of one over. On the right-hand side here, you have 1 over the rate. So this is this number here. So this is like the decay time. So if the field is very large, you have a small decay time. And the solution to this breakdown of the Born-Oppenheimer is retardation effect. So here you have the nuclei. They move on a time scale, say 1/2 vibration period, which scales like square root of mass. Now the exit point, which we calculated earlier, it was called Z0 in my initial slide, is given by the ionization potential over the field. So this is the exit point. And then I can ask myself, how long time does it take for the electron to reach this exit point? Well, it's 1/2 times acceleration times time squared. It's this formula here. From this I get the time. Now, if the time it takes for the electron to get to the exit point is the same or comparable to the time it takes for the nuclei to vibrate, the electron motion is no longer fast compared to the vibrating motion. So therefore, you would expect that if these two are similar, mathematically we just do them equal, then I would expect the breakdown of the Born-Oppenheimer. So I take this T here and I take this delta T here, and then I can get the field, and the field scales like 1 over square root of m, and that's this thing you see here. So this is the retardation effect. There are some newer papers on all this tunneling theory. It turns out that including what we work on actively now is to do more on nuclear motion. This has not been done, to my knowledge, in a way where you try to include that at the same level as the electron motion. So this is what we're trying to do now, analytically also. And let's look at the outlook. Tunneling is the initial key step. I have given you a lot of formulas with the hope that you should now be better prepared to understand what enters the theory of tunneling, and therefore you should also better understand when you can apply it and when you cannot. Tunneling theory is needed to interpret results of total ionization yield as function of molecular alignment and ionization. Tunneling theory is used in combination with classical propagation, or maybe with or without action phases, so you can do a little bit better. This here, I think, is true. The tunneling theory for molecules, including nuclear motion, is not well explored, but it's very relevant and timely to do. In the 90s, there were papers also from Paul on imaging of vibration wave patterns. The interpretation was in some classical terms. What are the quantum effects from the type of reasoning that I have followed in this talk? That's one of the questions that's driving us presently. And please, if you like, think about the exercises, think about the secret state, the weak field, the dipole stuff, the separation, the matching, the geometry. Think about the Born-Oppenheimer. It's really stimulating to think about these timescales also when you have the external field. And with that, I'd like to thank again also the collaborators on these type of funding things, and also the experimentalists, which I didn't mention here, but from time to time we've been lucky to collaborate with experimentalists. That's great pleasure. And also I'd like to thank the funding agencies. Yes, that's it.
Yeah, we have time for a few more questions, yeah.
Yes, so what you showed was for small gamma. So you took the field somehow as a parameter in the Schrödinger equation, and you introduced this complex energy E of F. So can you make some statement what would happen, or can one somehow express or solve or draw some conclusions about what happens when gamma comes close to 1, and so the field is somehow time dependent but not very fast? So Where does it break down? At which point?
Yeah, in this talk, in fact, exclusively in this talk, I just assumed that the field was static. And your question is about when is that a good approximation? And this I only mentioned briefly, saying that maybe this Keldy's parameter should be small. And I also said that it's not enough that that's small. You also need to have a frequency which is small compared to the binding energy of the electron, so that the electron moves extremely fast while the field changes direction. But I have not quantified under what circumstances this tunnel theory is correct. This can be done rigorously in something called adiabatic theory, which has been developed by electrosticking here and tool. And that's beyond the scope of this talk to go into it. And I cannot give you a better, clearer answer at this point. But it's a matter of looking at these parameters, omega over naught, and then look at the corrections.
Okay, but is there any way to somehow solve this problem or tackle this problem in the intermediate regime, where you are not strictly adiabatic?
Then you introduce more and more non-adiabatic corrections, of course. And then we always have the TDSE if we have only one electron we can solve it. So no, I think there's no easy way to do that. There's no easy way to do that. It also depends on what you want to do as a theoretician. I mean, you can of course always design and build up some models somehow that can capture some things. But a lot of that does not necessarily follow directly from the Schrödinger equation. If you want to, but it could be fine to do it, because if you can compare with the experiments and you can see that you can explain this and this, it's of course perfectly justified. But it's also related to a matter of working style, obviously. If you want to try to do things that follow more or less rigorously from the Schrödinger equation, or if you want to build by hand more.
Okay, thanks.
Yeah.
I have a question about the structure factor. Yes. The two states. So you could also have intermediate cases, right?
Sure.
So
yeah, well, there's a different angle between
yeah.
the external field.
So is that monatomic between those two, or is there minimums or maximums as it
that could be minimum.
Okay.
That's one question. So when we do the calculation, we have to calculate that structure factor for each annotation. So if you if I have a 3D object, I want to specify how it's oriented in space, I need 3 angles. Typically we use the Euler angles. So it's something about rotation around the laboratory fixed z-axis, rotation around the new y-axis, and then rotation around the new z-axis. That's delta, beta, and gamma, or theta, phi, whatever. So now in our case, I think you can see that it cannot depend on alpha, because the field is homogeneous. And in some cases, it's also independent of rotation around the molecular axis, right? Because if it's, for example, a sigma state, there's no way. So then it's only this beta angle, namely the angle between the field and the molecular axis. But then we have to calculate the structure factor for each value of beta. So this can be done. And then what we have done, for example, in one of these papers, in this catalog, in this catalog here, where you find most diatomics, you get coefficients which you multiply by the Charlotte polynomials, and then you can construct all the structure factors you
Yeah.